I'd like to thank everybody for the opportunity to talk at Target Multiplai 2023. I'm going to be talking about my favorite topic, the next generation of AI, from machine learning to sequential decision analytics. This is sort of an overview of all the projects that I've worked on in my life. I did a lot of work in the trucking industry, also with rail and air cargo, but I've done a lot of work with logistics and supply chain management, e-commerce, health, energy. These are all fabulous problems that can all be described as human processes. And these are problems that combine decisions with uncertainty. And it covers every aspect of what we humans go through. Generally, we're making decisions to improve various goals and objectives, maybe increasing profits or reducing cost. But maybe I want to reduce my carbon footprint or maximize productivity or improve employee retention. If you want to run a better system, process, whatever you want, you have to make better decisions. So the first question, which is often overlooked, is what decisions do you have to make? And then secondly, how do we make better decisions? Well, perhaps we're going to use artificial intelligence. So here are a number of situations that we see over and over again of a room full of people sitting at computers making decisions. Now, in the 1990s, this was very exciting and high tech. Today, not so much. It looks more like a Model T assembly line, early 1900s, which was a great breakthrough when it was first introduced. But now we're sort of hoping for something better, such as a Tesla production line. So here's where robots are acting on a chassis. We would like to automate the process of humans making decisions and acting on the information. So let's go through, start with the 7 levels of artificial intelligence. We have 7 levels of artificial intelligence. The first 4 can be broadly described as making computers behave like humans, which we've long considered to be sort of the high watermark of intelligence. Then I'm going to talk about 2 more levels. This is where we want computers to be smarter than humans. So let's start at level 1, rule-based logic. So in the 1960s and 70s, this was the first artificial intelligence. This was the first AI. And we thought computers were going to conquer the world. And this could handle simple problems like if eating red meat, then drink red wine. But when we got into, say, a medical application where if it's a male patient over 60s, high blood sugar, overweight, brown eye, this is too many combinations, and it just didn't scale. And by the 1980s, it was being considered as quite a failure. The reality is that while rule-based decision-making didn't take over the world, it's widely used. It's a very powerful tool. The next 3 levels all have something to do with machine learning. So basic machine learning that goes back to the 1900s, this is estimation, inference, and forecasting using what are known as lookup tables, parametric and non-parametric models. Early 2000s is when pattern recognition really emerged, image recognition, voice recognition. Is this a flower? Natural language processing. And this was all using this technology known as deep neural networks. And then in the 2020s, we've started to see these large language models, ChatGPT. This involves training on genuinely massive data sets, and we're training colossal neural networks, 500 billion parameters that can turn a few words into an entire essay. Now, let me talk briefly about machine learning as an optimization problem. So let's say that we're trying to come up with a function. Maybe we want to predict demand as a function of price, and somebody comes in, and this actually happened to me, says, oh, let's just fit a line. And I say, okay, fine, give me the data and we'll fit the best line that we can. Now, somebody else may come in and go, oh, no, it can't possibly be a line. It has to be an S-curve. And I'll say, okay, fine, let's take the data and fit the best S-curve. Now, today, somebody's going to come in and say, well, what about a neural network? And I'm going to urge caution because neural networks can overfit the data. But whatever you want to choose, you're going to be looking at these 3 broad classes of functions, and you're going to want to try to find the best function and use some sort of big data set to fit the data to the function. Now, let's go back to my range of problems. Behind every one of these applications are decisions, and every box is a question that's posing a choice where there's multiple choices, and I want to make the best choice. So it's my decision of what to choose. Now, there's 3 broad classes of decisions. Decisions acting on physical resources like managing inventories, building facilities, assigning drivers, scheduling workers. Financial decisions, cash flow management, pricing decisions, investment, insurance contracts. And then we have decisions to move information, sending and receiving information, marketing and advertising, running an experiment as a way of collecting information, product testing. Now, we can have decisions that are strategic in nature, off into the future, tactical planning, ordering products, say, from India that arrives weeks and weeks into the future. And then we have the real-time execution decisions, like which driver should move a load, which production line should be working, or spot pricing decisions. Now, these decisions can also be made at any level in the organization, the C-suite, middle management, field operations. My major point here is when I say the word decision, I mean any decision with any application made by anyone in the organization. Now, let's talk about the first of our decision-making technologies. This is level 5, deterministic optimization. Now, deterministic optimization involves a vocabulary that may not be day-to-day English, but thousands of students around the world graduate every year speaking exactly this language. And it's all due to one particular book that dates back to the 1950s, George Danzig, who made this particular modeling language useful by inventing the simplex algorithm. So let's talk about a simple problem like finding the shortest path. These are called low-dimensional decisions. I'm at node 2. I should go to node 5. Or I can do high-dimensional decisions like where to locate a warehouse or manufacturing facility, where I have to look at all the permutations and combinations around the world. Now, this basic language allows me to go to complex problems like designing a supply chain and come back with responses of, okay, here's the best supply chain. Companies can use deterministic optimization to plan their supply chain. So let's take a problem where I'm looking at perhaps getting a product from China, and it costs $18.40 and $5.20 in shipping, but maybe I want to get that same product from India. It costs $18.70, $3.80 in shipping. If I compare the two, in this case, India comes out cheap, less expensive. So this is an instance of deterministic optimization. Now, this is a low-dimensional problem. I can do this on a spreadsheet, but maybe I have manufacturing facilities all around the world, and I have to juggle capacity constraints. That's a high-dimensional decision, and companies would use these tools of math programming. So now let's come back to my wide set of problem applications, and we have all of our various decisions that we have to make, and that's quite a wide range of decisions. After I make a decision, new information comes in that I didn't know when I made the decision. So all of these are what are called sequential decision problems. You make a decision, then new information comes in. Make another decision, more information. And the information that arrives when after a decision is made is not known when the decision is made. So we have to make decisions under uncertainty. So here's an example, inventory planning decisions. I can place an order for inventory. Maybe it arrives very quickly, or maybe it arrives days or weeks into the future. Then I observe the demand, but now I make another inventory decision and observe more demands, and so on and so forth. So this is a classical sequential decision problem, one of the most famous in the academic literature. I now work with a company, Optimal Dynamics, that assigns drivers to loads. The circles are driver and the squares of loads. And these evolve over time as shippers call in new loads. And there's also new information about weather delays and driver behavior. Maybe in health, I'm shipping new vaccines, and I have to do vaccine distribution. I have to decide how much vaccine to ship, to where and what type. And then I observe how the market responds and how many people accept the vaccine. And of course, we can't forget finance because I'm buying and selling investments and stocks while the prices are changing over time. Let's take a very simple problem. I'm going to start with an asset where I have to buy, sell, or hold. So very simple decision. Then the price goes up, down, or stays the same, and so on and so forth. I can buy, observe price changes, buy, and observe price changes. And this problem explodes with dramatic speed. And this is a toy problem. This is an absolutely trivial problem. Think about all the problems I just illustrated and looking very much farther into the future, and you see how complicated these get. So let's talk about modeling sequential decision problems. Whenever you have a physical problem and you want to put it on the computer to use AI, for example, you have to go through the step of modeling. Now, if you have a deterministic optimization problem or a machine learning problem, everybody trained in these fields learns how to sit down and write out their problem on a sheet of paper. This is not true with sequential decision problems. We lack a standard modeling framework for sequential decisions. We enter what I like to call the jungle of stochastic optimization. Every one of these terms is a separate field. Behind each field is at least one, often several, sometimes many books. You can get a PhD in any one of these fields and spend years of your life. Some people spend careers in one of these books. So let's talk about how to model a sequential decision problem. I'm going to make all of you experts. So we're going to start up top where we have a state variable. A state variable, that's the word we use, is all the information we know or believe. You may have information about quantities and parameters you don't know perfectly. You then make a decision that I've illustrated before, and then new information arrives that I didn't know when I made the decision. Each time you make a decision, we receive a contribution or incur a cost. Decisions are made with a method that I'm going to call a policy. It's the most widely used term in English. Now, this is some method, but I'm going to design it later. And this is the major point of departure with my modeling framework, because all of those other books all have a method. They're coming to you with a method. Think of it as a hammer looking for a nail. Now, after I've made a decision and observed the new information, I have something called a transition function that tells me how to update the state variable to the next time period. This can be thousands of lines of code. And finally, the goal here is to find the best policy. Now, I like to put all these together in a list of 5 elements. And I can take any one of those applications, any sequential decision problem, and lay it out in this notation. So there on one PowerPoint slide is a modeling language. And certainly in a country like India, with all of your diverse languages, you can appreciate the power of having a single language. And furthermore, this language covers every one of those books. So this is a truly universal modeling language. Now, let me talk briefly about this thing of optimizing over policies. Policies consist of 2 elements. One is the structure of the policy, and that's normally chosen by a human. That's like that machine learning problem. It could be a line or an S-curve or a neural network. Human has to choose that. Then a computer comes in and says, oh, those tunable parameters, we have algorithms for that. And finally, I have to evaluate the policy by simulating, and I really like it when I can simulate in the computer. Now, let me build this bridge between machine learning and sequential decisions. In machine learning, we're looking for functions. They're called statistical models, and they fall in one of those 3 circles. With sequential decisions, we're also looking for functions. We call them policies or methods for making a decision. In machine learning, in order to evaluate the function, I need a training data set. With sequential decisions, I do not need a training data set. I need a model of my physical problem. And this is the key point of departure. When we're doing optimization, I need to know about the problem itself. So let's talk about how do we search over policies. Now, there's a 6-step process that I like to use, starting with an application. I really like it to have an application. And then step 1, I ask 3 questions in English. What are your performance metrics? What types of decisions are you making? What are the sources of uncertainty? Now, let's say you're not a mathematical type. You don't do programming. You just have good, complicated problems to solve. I claim you can't think about your problem until you answer those 3 questions, because for me to build my computer model, I can't get to first base until I can answer all 3 of those questions. Then step 2, I fill out the remaining 5 parts of the model. Step 3, I have to get into this complex area called uncertainty modeling. Step 4, I talk about designing policies. Step 5, build my computer model to test and evaluate the policies. And then step 6, take it to the field with implementation. So let's pause a little bit and talk about uncertainty. So in my new book, I've identified 12 classes of uncertainty. Now, these 12 classes are from the perspective of modeling. That is, every model has these 12 classes. And what you should do is compile a list. You may have a relatively simple problem that doesn't involve all 12 classes, maybe just 1 or 2. If you have a complex problem, like a supply chain, like an energy system, like a health system, you're going to need all 12 classes. And what you have to do is take the 12 classes, take your particular problem domain, and go down category by category and saying, what do I have that belongs to this category? This is an incredibly rich topic. You could easily spend a career focusing on this. Companies specialize in this. And it's so rich, I'm not going to say anything more. I'm going to go to designing policies. So when designing policies, first of all, we make decisions X using a method called a policy. I get a lot of questions that ask me, what is a policy? Well, a policy is a method that makes a decision using the information in the state variable. Any method. Now, I like to think of a policy as like a locomotive engine. A steam engine turns the energy in coal into a force that propels the train forward. Policies are the engines that turn information in state variables into the decisions that drive companies. If you stop making decisions, the company will slowly come to an end. State variables are like the energy going into the engine. It's just that state variables are much richer. It's more like a buffet with all different types of food. And so you have very rich and complex databases for storing all the information in a state variable. But it's basically the energy that moves the company. There are two fundamental strategies for making decisions. The first is called policy search. These are when we have classes of functions, and I want to search over the functions to find the one that works best over time. And secondly are the look-ahead approximations. This is where you say, okay, if I make this decision, I'll earn a cost or reward, and then downstream, I'll have to think about what happens in the future. And I'm going to plan the path all the way into the future. Now, each of these two strategies I can divide into two classes, creating what I like to call the 4 classes of policies. The first is PFAs. These are the simplest policies that all of we humans use on a day-to-day basis. Buy low, sell high. If the inventory falls below some number, order up to a number. If it's cold, wear a coat. This is how we humans get by making our decisions. Now, it's only for fairly simple decisions. For somewhat more complicated decisions, very popular in industry is what I call cost function approximations. Now, this is a term that I've introduced, but this is well known to industry. This is where you take a simplified optimization model. So here we have these complex problems in business. I'm going to turn it into a simplified optimization problem, and then I'm going to go put in some tunable parameters like buffer stocks, or airlines have to put in schedule slack. These little tuning parameters that make my deterministic solution work well over time. This is very comparable to what we're doing in parametric statistics. The policy search policies are the simpler ones. In the look-ahead class, we have policies based on value functions. I'm in some state. I have a truck. I dispatch him on a load. He arrives at the destination. What's the value of the truck at the destination? If I can capture the future in a simple estimate of the value, makes the problem a lot simpler. Coming up with that value can be hard. And then the last class is the direct look-aheads. Google Maps is my best example. You plan the path all the way to the destination in order to figure out what to do now. Now, as the network changes, Google will update the path, but it's always planning all the way to the destination. So these 4 classes of policies I claim are universal. I claim it covers any possible method for making decisions. This means it includes what you're already doing today in your company. Now, you can build policies through hybrids. I will also tell you these 4 classes includes any method in the academic literature, including policies that haven't even been invented yet. These are called meta classes. So this is a general toolbox that allows you to go to any problem and come up with the best practical way for making decisions. So let me go back to my bridge between machine learning and sequential decisions. So we've just identified policy function approximations. All the methods under PFAs represent any possible function you might use in machine learning. So if you restricted yourself to just to PFAs, this is very much like machine learning. It's just that instead of using a training data set, you're going to train it with a model. But I still have 3 more classes of policies, and you're going to need all 4 of these. Now, let's take a simple inventory problem where I have an inventory in a warehouse in Atlanta, and I have to place an order, and I'm going to use a simple order up to inventory policy. Inventory gets down to a level, order up to another level. Now, what can happen is as the ships of cargo coming in from the Far East might run into a storm. This might be random information coming in. Now, I could make the decision to ship it via air freight. I have a rush order just to make sure that I don't run out of stock. I can reroute the ship up to Vancouver, and instead of running it in by train, I can put it on truck. So now we see an interplay between new information coming in and decisions that I can make. So we put together a set of 6 different samples of this problem by changing the data and making them different characteristics. Then we created 4 different types of policies. The first is a simple order up to SS policy. The second one is a widely used, it's an SS policy adjusted for lead time. And this is probably the policy most widely used in practice. But then we have direct look-aheads, where, like Google Maps, I'm planning into the future deterministically. And I have a stochastic look ahead where I plan in the future, but I plan capturing the uncertainty. Now, yellow here, these are the ones that work best. The number in the square is a measure of how well that policy works. Yellow is best, tan is second best. And we can see that each of the 4 classes of policies work best on at least one of the problems. The tan is the second best, and we can see that the adjusted SS policies, if it doesn't work best, it's second best on all the problems. And that's very encouraging because this is what people tend to use in practice. Now, if you look at all of the books that people use to study inventory and supply chain management, and these have varying levels of technical material, not one of these books will show you how to model a general stochastic inventory problem. So we have work to do. Now, picking which of the 4 classes is actually quite a challenge. I have a chapter dedicated to this that talks you through how to do the trade-offs. This is something that takes experience. Generally, there's a trade-off between how hard it is to design the policy and how hard it is to compute. Now, let me divide my 4 classes. Let me split the 4th class into 2, deterministic look-ahead and stochastic look-ahead. Now we have 5 types of policies. Which are the most useful? So category 1 is far and away the most useful. This is absolutely what companies tend to be using: the PFAs, the simple rules, the CFAs, and the deterministic DLAs. I can guarantee you the companies are already using this. Now, category 2 is where I need to look in the future and explicitly plan for uncertainty. These are much less used, but they are used and sometimes have to be used. And that third category is the policies based on value function approximations. And this goes under names like approximate dynamic programming, reinforcement learning. I have a 500-page book on category 3. I spent 20 years of my life. It's a very, very useful policy on a very small set of problems. I am here to tell you category 1s are the ones that you most like to use. So let's take the ones in category 1s and compare to machine learning. In machine learning, I'm searching over different functions like the linear or the S-curve, and then I have to tune the parameters using my data. Parameterized policies, I have my PFAs, CFAs, and deterministic DLAs. Those are my category 1 policies, and I still have to do parameter tuning. So we see these close parallels. This is not how this material is taught in the literature today. So I'm going to push that I think we need a new educational field that I'd like to call sequential decision analytics. Now, teaching decision analytics, there's 3 core disciplines: optimization, machine learning, and simulation. These are very well known, many books. No matter where you take your courses, you're going to learn roughly the same material. Once we get to sequential decision problems, it's a mess. There's no one book in this jungle of stochastic optimization. The books do not teach the same techniques. They have about 8 different notational systems. It's a mess. I've come out with a new book last year. This is a technical graduate level book. It's for engineers who want to write code. It's not for theoreticians who want to prove theorems, but it is for technical people. I also have a book that I wrote for an undergraduate course that uses a teach by example style. And this is for a broad audience. It's available as a free download from this website. If you want just the PDF, you can also buy it. There's instructions at the webpage. It's a fairly low-cost book. But this is a book easy to skim. All but 2 of the chapters are on different examples following the same general style. Now, I think it's time to start teaching sequential decision analytics. Major companies, I think, need to go to your local universities and say, look, we need people taught in this field. But you don't have to wait. You can also teach it to yourself. I have a web page dedicated to different styles for teaching this material. There's also an introductory seminar that I think companies can do an in-house weekly seminar on their own. This is not something that I teach. I have the guidance there. It's based on the undergraduate book, which again, you can download. And then there's an advanced seminar for the more technical. This is based around my big book. So I'd like to thank everybody for attending the talk. Here's a series of URLs, but if you wish the last URL, tinyurl.com SDA links, is a web page with all of the other links. So if you just remember tinyurl.com/SDA links, that has all the material. Thank you very much.